Okay, in this video we're going to be looking at the nth term test. This is a test only for divergence. The nth term test does not show convergence. So this is a nice quick test to see very quickly if a series diverges. It will not show you convergence though, only divergence. This will be added to our our telescoping series and our geometric series test that we already have. So if we say if the sum n equals 1 to infinity of a sub n, that's less than infinity, that's just a way of saying that the series converges, then the limit as n goes to infinity of a sub n is equal to 0. If the series converges, then the seed sequence goes to 0. So the idea of the proof is we go ahead and suppose that the sum as n of n equals 1 to infinity of a sub n is equal to L. Then what that means is if we say a series converges, then that means the limit of the partial sums, which is S of n, is equal to L. Alright, and then we make the argument since S of n is equal to S of n minus 1 plus a sub n, S of n is a1 plus a2 plus all the way out to a sub n minus 1, a sub n. It's just the first n terms of this series. The sum of the first n terms of the sequence, I guess we can say. S of n minus 1 is going to be a1 plus a2 plus all the way out to a sub n minus 1. So we can say that S of n is equal to S of n minus 1, but we're missing the last term, the a sub n, so we need to add that in. If we take the limit of that, the limit as n goes to infinity of S of n is equal to the limit as n goes to infinity of S of n minus 1 plus a sub n. If we split that limit up, we know that the limit as n goes to infinity of S of n is L, and the limit as n goes to infinity of S of n minus 1, it's going to go to the same place, that's L. So we have L is equal to L plus something else. That something else has to be 0. And so that argument is the a sub n's limit must be 0. Okay. Thus, the limit as n goes to infinity of a sub n is 0. We're going to use the contrapositive of this theorem. So the original theorem, we have P, which would be the sum converges, implies Q, and Q is the limit of a sub n is 0. The contrapositive is not Q, which is the opposite of Q, which Q is the an went to 0, that would be an doesn't go to 0, implies not P. And so a sub n was the summation a sub n converges. That was P. So the negation of that would be it doesn't converge or diverges. And so that's what we have there. That's our nth term test there. If the limit as n goes to infinity of a sub n is not 0, then the sum n equals 1 to infinity of a sub n diverges. Okay. We're going to look at a couple examples here. Okay, so we're going to determine the convergence or divergence of each series. So we're going to look at the sum n equals 1 to infinity of n over 2n plus 3. Now, probably one of the first series tests I'm going to look at very quickly is the nth term test. A lot of times you can look at it visually and just say, okay, the limit of the seed sequence is not 0, divergence by the nth term test, and then you're done. Right now we only have two other series tests. We have the telescoping series, which this is not a telescoping series, and it's not a geometric series, so then we can't use either one of those tests. So the only one we have is the nth term test. So we're going to take the limit as n goes to infinity of n over 2n plus 3, and then using what we know about horizontal asymptotes, this has a horizontal asymptote of 1 over 2, and so that's the limit. That limit is not 0, and so because that limit is not 0, this diverges by the nth term test. Now let's say, for example, that this limit was 0. If this limit was 0, the nth term test doesn't tell us anything. It's inconclusive. We'd have to go use a different test. Okay. All right. In the next example, I can't give you like a proof, but I can give you a numerical argument for the divergence. Later on in this next example, we can show that we have a divergence using the ratio test a little bit later on. So we're going to do a numerical argument for the next problem of why the a sub n goes to infinity. So we're going to compare n with n factorial and 2 to the n. Okay, so if n is 1, 1 factorial is 1, 2 to the first is 2. Okay, 2 factorial, 2 times 1 is 2. 2 squared is 4. 3 factorial, 3 times 2 times 1 is 6. 2 to the third is 8. 4 factorial, 4 times 3 times 2 times 1 is 24. 2 to the fourth is 16. So right now, it looks like the exponential was winning up to 4. Now it looks like the factorial is starting to overtake. Now let's look at 5 factorial. 5 times 4 times 3 times 2 times 1, that's 120. 2 to the fifth is 32, so it looks like the n factorial is starting to outpace the exponential. 2 to the 6, not 2 to the 6 is going to be 64. 6 factorial is going to be 720. So 2 to the 6 is 64. Okay, 7 factorial is 5024. 2 to the 7th is 128. And looks like factorial is leaving the exponential in the dust now in terms of how fast it's growing. Okay, let's do a couple more. 8 factorial is 40,320. 2 to the 8th is 256. 9 factorial is 362,880. 2 to the 9th is 512. 10 factorial is 3,628,800. And 2 to the 10 is 1024. And so n factorial is certainly winning the race to infinity here. And so what we're going to do is we're going to use this because the series we're going to consider is going to be the sum n equals 1 to infinity of n factorial over 2 to the n. And so we have our column set up there, or our table set up here, and we can go ahead and find these quotients quite easily. So it's going to be 0.5 and 0.5 and 0.75, so relatively stable so far. And then 1.5 and 3.75, so we got a little bit more growth. And then 11.25, so that's it's getting larger now. And 39.25, so it's getting larger. And 157 and 708.75, 3,543.75, and so that certainly does not look like that is going to 0. It looks like it's going off to infinity. So the sum n equals 1 to infinity of n factorial over 2 to the n, I'm going to make the argument based off of my numerical results that because a sub n doesn't appear to be going to 0, as n goes to infinity, we can conclude that we have divergence by the nth term test. Okay. And so this tells us a little bit about how factorial grows. Factorial grows much faster than exponential. At the beginning, they look fairly comparable, but I would say once we got to 5, the exponential is going to be left in the dust compared to the factorial. Okay. All right, let's go ahead and look at one more here. So we'll look at the sum n equals 1 to infinity, natural log of 1 over n. Again, this is not a telescoping series. This is not a geometric series. The only other test we have is the nth term test. So we're going to look at the limit as n goes to infinity of the seed sequence, which is the natural log of 1 over n. We're going to go ahead and sketch the graph of the natural log of x. And as n goes to infinity, 1 over n is going to 0 from the positive side, and the graph of natural log of x is going to minus infinity. And so that's what this limit is going to be. And that limit is not 0. and so because that limit is not 0, we can conclude that this diverges by the nth term test. Okay. Had the limit been 0, the nth term test doesn't tell us anything. So the nth term test will only show us divergence. Okay. If the limit of a sub n is 0, then it's inconclusive, which means we got to try a different test. Okay. All right. Stay tuned for the next videos on the integral test and p-series. So we'll see you next time.